In the last video, we looked at how we can convert open chain monosaccharides, such as this molecule, open chain D-glucose in the middle, into ring structures through intramolecular reactions, where we react the aldehyde group at one end of the glucose molecule with the next to the last hydroxy group down here, where during the reaction, the hydroxy group uses one of its sets of lone pair electrons to come up and attack the positively polarized carbonyl carbon, forcing the pi bond out onto the oxygen, ultimately yielding in the final product a six-membered ring, which I'm outlining here in our final product, with a hemiacetal group at the location I'm placing a star on. I show this as two different equilibria reactions, one going toward the right and one going toward the left, with the difference between the two being that where the hemiacetal group is formed, there are two possible stereochemistries. One in which the hydroxy group at this newly formed chiral center in the product is oriented downward on the left, and the other on the far right, where I've just put a red star, where instead the hemiacetal hydroxy group is oriented upward relative to the carbon that it's bonded to. So as a consequence of this cyclization reaction, there forms a new chiral carbon at this particular location. This original carbon of the carbonyl becomes chiral here, and it becomes chiral here. There are two possible stereochemistries to that, and that is an important consideration when we think about the function of these cyclic sugar molecules. Additionally, there are other chiral centers within the molecule, here, 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 and here, that remain untouched during the reaction, meaning that at each of these four chiral centers that I'm highlighting in my open chain glucose structure, nothing has happened directly at any of those carbons, so the RS configuration, the chirality in other words, remains the same. But we need a way to be able to draw quickly the chirality at each of these original chiral carbons, as well as at the newly formed chiral carbon in these cyclic structures. The way that we do that is by using a Haworth projection. A Haworth projection we can think of as being analogous to the Fischer projections that we used to show the stereochemistry of acyclic monosaccharides, such as the glucose molecule in the middle here. The Haworth projections are going to be the way that we show the stereochemistry of the cyclic form of these molecules. And at any given point within the body exists an equilibrium mixture of the open chain form of any particular sugar, as well as the hemiacetal form or cyclic form here or here in the case of glucose. By the end of this video, you will know how to systematically take the structure of any 6-carbon sugar with an aldehyde group and convert that into its cyclic form using a Haworth projection. Let's go ahead and take a closer look. There is a handout that goes along with this video, which you may find helpful to download because it includes the text that we feature here as well as some illustrations as we go through. Now, we keep in mind Fischer projections are the way that we represent acyclic molecules to represent the stereochemistry of those. So the structure of D-glucose on the left is a Fischer projection. The structure on the right that we're going to learn to draw in this video is a Haworth projection. Both are important because they allow us to represent the stereochemistry of sugar molecules, with Fischer projections being used for the open chain form, Haworth being used for the cyclic form of those sugars. We see that the alcohol group here reacts with the aldehyde group here to form the ring that we see in the final product. In this video, we're going to focus on how we go about orienting the hydroxy groups and other groups that are around chiral centers within these rings. So within the handout that corresponds to this video, we will use as our examples these two open chain sugars, and by the end of the video, we will have converted them into their hemiacetal cyclic form. The structure on the left here is a representative Aldo Hexos. We call it an Aldo because it has the aldehyde group, Hexos because a grand total of 6 carbon atoms. This particular molecule, as a throwback to earlier materials, since the hydroxy group at this final chiral carbon, as we go down the chain, is on the left, we would refer to this as an L sugar. The aldopentose example, on the other hand, is a D sugar because that final chiral carbon has the hydroxy group on the right. We will show during this video how we can go about representing the D versus L configuration when we draw the ring structure of a sugar. We will also look at how we can draw the configuration of each of these other chiral centers within the molecules as well. So let's take a look at the next part of this. The next thing we need to do in order to convert those acyclic structures into their cyclic counterparts as a Haworth projection is we'll draw the Haworth skeleton of a general hemiacetal hexose or pentose. So this structure here with 6 carbon atoms in the ring will be our general template that we will use for the hemiacetal hexose. And we see the word hemiacetal with reference to sugars. What we're referring to is that the atoms have formed a ring because that ring is an essential part of it, has a hemiacetal group. So this is our hemiacetal hexose with 6 atoms in our ring. On the right, we have our hemiacetal pentose with 5 atoms in the ring, including the oxygen atom. So these are going to represent our skeletons that we will decorate. So the first step in drawing the cyclic form of these sugars is to get familiar and comfortable with drawing structures that look exactly like these, where pretty much you draw a hexagon, place an oxygen atom in this upper right corner of the hexagon, and as an optional feature that you will commonly see and should be able to recognize, oftentimes these 4 carbon atoms that are facing us like this are shown as wedges to represent that the molecule is laying with these bonds coming toward us here and here. You can also draw those as straight lines. That would be completely okay as well, rather than showing them as wedges and dashes. Analogously over here, we have these bonds that I've highlighted in yellow that are pointed toward us with this wedge here that I'm highlighting here and the wedge highlighting here is what's showing that those bonds are pointed toward us. You could show those as just standard lines to make a pentagon there as well. In your pentagon, at that 12 o'clock position there in the top center, there will always be an oxygen atom. And then around the ring, at all positions other than where the oxygen atom is filled in, draw a vertical line here that goes above the carbon and below the carbon at each position all the way around. That's a perfectly vertical line at each of those positions. So in other words, in a pentose, it's going to be a vertical line up and down from each of the 4 carbon atoms of the ring, 1, 2, 3, 4. In the hexose, it's going to be a vertical line up and down from each of the 5 carbon atoms of the ring, 1, 2, 3, 4, 5. So now that you have that Haworth skeleton drawn in for a generic hemiacetal hexose or pentose, the next thing we need to do is start decorating that to represent whatever monosaccharide we wish to draw. Let's go ahead and take a look at that for our example problem. So when we are taking a look at drawing in the parts and pieces of the Haworth projections, the next thing we want to keep in mind is whether the molecule is an L sugar or a D sugar. If the molecule is an L sugar, that automatically tells us that we need to place a CH2OH group below the ring on the carbon immediately to the left of the oxygen atom that's in the ring. If it's a D sugar, the CH2OH group goes on the ring immediately to the left of the oxygen above the ring. So take a look at our example problem here. CH2OH here is bonded to the carbon atom immediately to the left of the oxygen in the ring. So here's our oxygen in the ring. We come to this carbon. This carbon is always going to be where there will be a CH2OH in these Aldo Hexoses or Aldo Pentoses, as is the case on the right. And in this, since the CH2OH group is down below that carbon atom, what that tells us is that this is an L sugar. L refers to the CH2OH group being below. You could think of the L there as being below. I put that L of below in caps to help us remember that L means below. On the other hand, the CH2OH group over here is above the carbon atom that it's bonded to. Here's the carbon atom in the ring, and that's above it. So CH2OH being above it will always indicate that the structure is D. So anytime you're looking at a cyclic sugar, you can immediately recognize whether it is a D or an L sugar by taking a look at the carbon atom that is immediately to the left of the oxygen in the ring and ask yourself, does the CH2OH group go up or does it go down? If it goes down, the configuration is L. If it goes up, the sugar is automatically D. And we can relate this back to our structure for the example problem we're looking at. Now I've brought in here our original structures that we are using as examples. In the case of the structure on the left, this was our hexos, so that corresponds to the ring up here. Since the ring up here has 6 atoms in the ring, it is a hexos. And in the case of this Aldo Hexos, we recognize that the configuration of this molecule would be described as an L sugar because the hydroxy group at that final chiral carbon with a star on it is oriented toward the left. And hence, when we come up to the top and we draw that as the ring, we need to put that CH2OH group oriented downward. In contrast, for our example on the right, our Aldo pentos in this case, the final chiral carbon going down the chain is right here. That OH group is on the right, and therefore that makes this a D configuration sugar. And up here, we draw that as D. So now that we have done that, we move on to the next step of looking at filling in each of the positions of our hexos and our pentos with the groups that need to be present. So next step is that at the hemiacetal carbon, the OH group there can be oriented either up or down because that OH group is newly formed during the chemical reaction. If you go back to the beginning of this video and you were to replay it, you would see that when we form a bond between the hydroxy group and the carbonyl group ultimately becomes a chiral center that has a new hydroxy group onto it. That new hydroxy group that originated from the carbonyl can be oriented either up or it can be oriented down, and both of those forms exist in nature. The sugar is classified as a so-called beta sugar if the hemiacetal OH group is oriented upward. On the other hand, it'll be classified as an alpha sugar if the hemiacetal hydroxy group is oriented downward. This seems a little counterintuitive to me because I always think of alpha as being at the top and beta being below. But in the system of naming and system of classifying cyclic monosaccharides, beta refers to up, alpha refers to below. So lock that into your mind here. So in the case of the structure on the left, this would be an example of an alpha sugar. And we've placed the symbol alpha there to emphasize that this is an alpha sugar. The way we recognize it as an alpha sugar is at this position, this is our hemiacetal position. The OH group is oriented downward. And if the OH at the hemiacetal position is oriented downward, the sugar is classified as an alpha sugar. On the other hand, in the structure on the right, this would be referred to as a beta sugar because that hemiacetal hydroxy group is oriented upward. So the OH group is above the carbon that it's bonded to, pointed upward, and that makes this classified as beta. If you were given the structure of a sugar, you could immediately classify as alpha or beta by looking for the hemiacetal carbon atom. That's the carbon atom that I'm placing a star on in black here and here, on the left and on the right. And if the OH group is oriented downward at that hemiacetal carbon, then it's alpha. If it's oriented upward, it's beta. And this is the hemiacetal position because it has an OH group bonded to it, and it's also part of the ether group. So that carbon is what drives whether this is referred to as an alpha sugar or as a beta sugar. And there is a critical term that goes along with this name or this classification, and that is the term anomeric carbon. The anomeric carbon is the hemiacetal carbon. So in the future, we may refer to the anomeric position, and when we do, it refers to this position right here that is the hemiacetal. It has the OH group and the ether group on that same carbon atom, and that can exist as two possible configurations. It can exist with the OH group pointed down or the OH group pointed up to give different stereoisomers. So now with these parts and pieces in place of our sugars, we can move on to the next step. At the next step, what we are going to do is fill in the H and the OH groups on all remaining carbon atoms of the ring based on their position in the Fischer projection. Now we will draw OH groups on the right in the Fischer projection, downward in the Haworth projection, hydroxy groups that were oriented on the left in the acyclic Fischer projection will be upward in the Haworth projection. That's quite a bit of material to think about all at once, so let's show how that corresponds to these Haworth projections that we've drawn for our example problems. So I've flown in the original example problems we were looking at, and we previously filled in the CH2OH group here and here as being below the ring in the structure on the left because our last chiral carbon had the OH group on the left here, versus having it on the right meant that it was above the chain here for the D configuration. So we established that it was D over here because the OH group was on the right. We established it was L over here because the OH group at that final chiral carbon was on the left. Now, our final task as we draw this N is to establish where the OH groups are located, up or down, at the other chiral carbons. The other chiral carbons, I will go ahead and number the chain here to represent where those are located. I'm numbering the chain starting from the aldehyde group in our original acyclic form, 1, 2, 3, 4, 5, 6. Remember that it is that first carbon atom that becomes the hemiacetal, and that's going to be true for both of these sugars. And so since that's the one that becomes the hemiacetal, we label as number 1 the position right here, because that's our hemiacetal carbon always of our Haworth projection. Then going around the chain, we go down to here to position number 2. That's our carbon atom number 2 right here. Following the ring around, position 3, position 4, position 5, and then carbon number 6 is that CH2OH carbon. So highlighting that to represent where it is located in our structure. We highlighted it blue up top, so I'll highlight it blue down below here as well. I'll put a little yellow on it also to give us a little further evidence about where it is there. So that's our CH2OH group. So we have our 6 carbon atoms here that form the ring. The OH group at position number 5 is what becomes the oxygen of the ring. So oxygen that we circled in green down below here becomes the oxygen of the hemiacetal ether. So how we go about orienting the OH groups is, now that we've systematically numbered our chain and we've systematically numbered our ring to match, what we keep in mind is that OH groups that were on the right in the Fischer projection will be down in the Haworth projection. OH groups on the left in the Fischer projection will be up in the Haworth projection. So matching that up, we look at position number 2 here of our Haworth projection relative to position 2 of our open chain form. And since in the open chain form, we saw that the group was on the right, OH being on the right in the open chain form means that the OH group is going to be pointed downward in the Haworth projection, in the cyclic molecule. So that's why the OH group is pointed downward here at position 2. We identified this as position 2 of the chain. It's position number 2 of the ring because we start numbering with the hemiacetal carbon. That was the aldehyde carbon originally. So at position 2 here, since the OH group was on the right in the acyclic form, it's down in the cyclic form. Going to the next position at position 3, the OH group is down there as well because the OH group here was on the right. And so that again means that it's downward in the Haworth. Coming to the next position, at position 4, position number 4's OH group was oriented to the left in the Fischer projection, and therefore in the Haworth projection, that hydroxy group needs to be oriented upward. And indeed, it is on the left. And then here at position 4, it's oriented upward. And then position 5 is where the ether bond forms. And so at position 5, that is what determines the D versus L configuration. And we looked previously and said that if it's L, then that means that the CH2OH group is going to be oriented downward. If it's D, then the CH2OH group is oriented upward to finish off drawing the Haworth projection of these molecules. So now, at this point, we have finished drawing the Haworth projections of this sugar molecule here, as well as we could also have done it for the sugar structure over here using the same guiding principles that when we are numbering our carbon chain here, 1, 2, 3, 4, 5, in the case of this 5-carbon sugar, starting with the hemiacetal 1, 2, 3, 4, 5, we keep in mind that if the OH group is on the right, it's going to be down. So right in the Fischer projection becomes down in the Haworth. On the other hand, left in the Fischer projection becomes up in the Haworth. So that's why at position 3 of our chain and position 3 of the ring, the OH group is oriented upward. And then at position 4 of our pentose, position 4 is where the hemiacetal group forms. And so that's why position 4 is where the CH2OH group is. And since it's a D sugar, we put the CH2OH group oriented upward. So with the steps that we have described herein, you can now systematically walk through the process of assigning the positions of each and every atom within the cyclic form of a sugar by starting with the Fischer projection of an acyclic open chain sugar. You can determine what the cyclic form of that sugar would look like. And by understanding the structures of these, we can then take steps toward understanding what the functions of those structures would be.